Hi everyone, my name is Siddhant Khurana. I am a friend of Abhishek Bhaiya here. Abhishek Bhaiya was my senior in college, and now he's also working on open source study. Uh, Something about me, I did my master's in aerodynamics from TUDelft, and in this session I presented my topic of my thesis in front of you. And I would really like to thank Abhishek Bhaiya and Open Source Study for giving me this platform where I can share my work and make it available for other people. Please feel free to contact me or Abhishek Bhaiya if you want to know more about the topic that I'm presenting. And please visit Open Source Study for more such interesting scientific topics that might be really good for you. And the topic of my thesis, as you see, is equivalent fluid modeling of a honeycomb acoustic liner using the acoustic porous medium formulation. So, yeah, you would think that it's quite a long topic and you wouldn't understand all the words that are mentioned in this topic. I had the same thing when I read it for the first time. But as we go through this presentation, you guys will find out what the problem statement is and what this topic actually means and which methodology we followed to solve the problem at hand. So this was the plan for today. Have some introduction and methodology. I'm going to skip the results and conclusions for this presentation. I think it's better if I focus on the introduction and the methodology we followed. If you are really interested in the results and the conclusions that I had from my thesis, you guys can go to my thesis, which is present in the TUDelft repository, and I think Abhishek will also put it down in the link or in the description of the video. Moving on, the context of the problem. So, you guys know already that aircrafts can be quite noisy. If you guys live near the airport, like me, you would know that how annoying it is to have an aircraft flying and it producing a lot of noise, and yeah, it's super irritating. It's so much irritating that even agencies within Europe are releasing noise certification level, which every aircraft needs to follow now. More so because, as you would know, there's a concept of air taxis and drones and quadcopters coming up, and these flying vehicles are expected to fly in residential places. So when residential places come into effect, the noise restrictions or the noise level certification becomes even stringent. And that's one of the main motivation also that why I chose this topic. Moving on. One of the major sources of noise in an aircraft is an aircraft engine. Of course, there are other noise sources such as flutter in the wing or other aerodynamic sources, but the aircraft engine is the biggest sources of noise. However, in aircrafts engines, they already have some technique to mitigate the noise which is produced by aircraft engine, and that is called as an acoustic liners. Now, as you can see, why acoustic liners? Because these damping technology is lined on the walls of the engine nacelle, as you can see in the black here. And my thesis or research in the topic of these acoustic liners. Now, acoustic liners can be of various type, but for the purpose of my thesis, I focused on the honeycomb liners. What are honeycomb liners? As you can see here, it is comprised of a perforated face sheet, a honeycomb cavity. Why honeycomb? Because the cross-section of this cavity is in the shape of a honeycomb, and it is backed by a solid backplate. Now, one measure to assess the performance of any acoustic liner is through an acoustic impedance. Mathematically speaking, acoustic impedance is shown as the pressure fluctuation divided by the velocity fluctuation at the perforated face sheet normal to the surface. If we go and spread this mathematical formula even more, we get something like this, which a real term and an imaginary term. And to understand this, I will show the following illustration. So assume there is a acoustic or there's a perforated face sheet, a honeycomb cavity, and a solid backplate. And we will first talk about the phase sheet resistance, which is represented by R. If an acoustic noise source goes and hits the perforated phase sheet, the noise level will be damped because of skin friction. And in addition, there can be some non-linear sources of damping, such as vortex shedding, as you see here. And all this skin friction damping and the damping due to, or let's say loss of energy due to vortex shedding, is covered by this term, the phase sheet resistance. The next term is phase sheet or mass reactance. Now, this reactance is basically the reactance provided by the mass of air present within the perforated phase sheet. And the last term, we also have the cavity reactance, which is the reactance given due to the depth of the honeycomb cavity. One assumption that I made in this thesis was that of a locally reacting assumption. So according to the locally reacting assumption, and it is quite important for the mathematical formulation that I just showed, whatever is happening or all the aerodynamic phenomena that are happening within one cavity, they are independent of what happens in another cavity. So a locally reacting assumption, it's all the aerodynamic phenomena are local to one cavity and are independent of the other cavity. Moving on. Now you know a bit about honeycomb liners, how their performance is assessed, and what the mathematical terms of acoustic impedance show. When we say about the motivation, we know that computational methods are one of the most popular methods for educing acoustic impedance. So usually if you want to assess the performance of a honeycomb liner, you will just make a geometry, run it in a CFD software, and you will get some results, and from there you can deduce the acoustic impedance of that liner. However, there are some problems in that. As you know, the phase sheet resistance, which is the biggest damping source of acoustic noise, is because it's caused by nonlinear vortex shedding and some surface skin friction. And if you really want to capture these aerodynamic phenomena in computational fluid dynamics, you need to really refine the geometry there. And refining the geometry means you have more grid points, and more grid points means that the simulations will be cost and time intensive. Imagine if you have to do it for a one aircraft engine which has thousands of perforated phase sheets or thousands of holes, let's say. This can be quite intensive, both for cost and time. So I think computational methods are lacking a bit here. There is one bypass of refining the geometry, and that is we use an impedance boundary condition. So an impedance boundary condition is rather than refining the geometry, we clearly give a surface and impedance condition, which is defined by this formula. However, it has been seen in literature and from our research that this mathematical formulation is full of numerical instabilities. So clearly, we have a need of developing resource efficient and stable methods for reducing acoustic impedance. And that brings us to our topic. But before I jump very deep into my thesis topic, I would also like to talk about equivalent fluid modeling, and I will take a bit of a detour here from honeycomb liners. So like honeycomb liners are some technology which is used for damping acoustic noise, we have one more technology which is called the porous material, which is just like a sponge in your house, and it is also used in various applications for damping noise. If you look closely into the internal structure of a porous material, you see that it is full of complex sub-millimeter scale holes. And if you want to do a CFD where you use grids to completely refine this geometry, you can already imagine how cost and time intensive it would be. So how an equivalent fluid, how a porous material, is used in CFD is using an equivalent fluid region. An equivalent fluid region is just a macroscopic representation of porous material. It bypasses the geometric complexities. It gives the same acoustic effects as a porous material. It can be easily coupled with numerical solvers, and it is fast and stable. So basically, in layman's word, rather than completely refining the internal geometry of porous material, we just put a block of fluid and just give it some conditions, some parameters, and we think that that fluid will have the same acoustic effects as the porous material. Moving on. Problem definition. You already know what a honeycomb liner is, and you, I think, also briefly know how it damps acoustic energy. And you also know about another type of acoustic damping technology, which is the porous material. And you also know that the porous material is modeled as an equivalent fluid region when it comes to computational fluid dynamics. Now, the challenge for us in this thesis is, can we use this equivalent fluid region to model the performance of an honeycomb liner? And yeah, that's basically the topic of my thesis. Moving on, the methodology that we followed. The research objective. So I have to determine a methodology to model the effects of honeycomb acoustic liners by implementing and validating the equivalent fluid medium. The research questions. What simulation parameters are required to accurately simulate the honeycomb acoustic liner and the equivalent fluid medium? Can the effects of a honeycomb acoustic liner for an acoustically excited flow be predicted by the equivalent fluid medium formulation? And what are the possible sources of discrepancies between the simulations and reference results, if any? The approach that I followed during this thesis. So first we do simulations with honeycomb liner in PowerFlow, which is a software, and we compare the results, these results of simulations with the simulations we do with equivalent fluid medium formulation, and we try to see if we get a similar match in our results or not. Perfect. Thank you guys. If you have any questions, you can write to me. I think Abhishek will also put my contact. You can look at my thesis in the TUDelft repository. Abhishek will also put that in the description. And it's a quite interesting topic. If you're interested in it, reach out to me. Maybe we can discuss some stuff about it. Thank you.